Welcome to Strength of Materials N5. Today's presentation is on compound bars and temperature-induced stresses. Before I begin, I want to say that all the notes I use in my presentations are available upon request. So for those of you who want to get the notes, you can just request them from me. Personally, I think it is better to watch the video having the notes in your possession instead of you trying to write down everything you see on the screen. Having said that, let us get straight into it. So first, for an introduction, what are temperature-induced stresses? Well, what you need to understand is that when you change the temperature of an object, let's say a metallic bar, then that change in temperature will result in a change in length. And it is either the bar is going to become longer or it will become shorter, depending on whether you are increasing the temperature or reducing the temperature. And so with that elongation or with that shortening of the bar, there will be stresses that will develop inside of the bar. And so let us say that delta T is the change in temperature, okay? And so it will therefore be equal to the final temperature. Tf is the final temperature and Ti is the initial temperature. So the change in temperature delta T is equal to the final temperature of the object minus the initial temperature of the object. So now, if the final temperature of the object is greater than the initial temperature, that will mean that the temperature has increased. And if the temperature increases, then the material is going to expand, okay? But if the final temperature is lower than the initial temperature, then the material is going to contract, okay? Because when the final temperature is lower than the initial temperature, it means that there is a decrease in temperature. Okay, so therefore the material will contract. Now let us say you have a bar, okay, so this is a bar and the length of the bar is L. And now let us say that we increase the temperature of this bar. Then what will happen? As we said earlier, if you increase the temperature, the material is going to expand because the final temperature is greater than the initial temperature. It means the temperature has increased. And if you increase the temperature, the material will expand. So in this case, the bar initially had a length of L, so that because of an increase in temperature, the bar grew longer, okay? And now this increase in length, we will call it delta L, okay? So this is the increase in length due to the increase in temperature. And so this change in length here can be calculated using this formula. Okay, so delta L will be equal to L. L here is the initial length of the bar multiplied by alpha. This alpha that you see is the coefficient of linear expansion, and then multiplied by the change in temperature, okay? So alpha, again, I say it's the coefficient of linear expansion. For those of you who did Science N4, Engineering Science N4, you are very familiar with this equation, okay? So alpha is the coefficient of linear expansion. Now, this alpha depends on the material that you are dealing with. What I am saying is that alpha will have different values for different materials. For instance, copper will stretch more for the same change in temperature than steel will, okay? And so therefore alpha for copper is bigger than alpha for steel, okay? So you have to bear in mind that this coefficient of linear expansion is a property of the material. So two different materials will not have the same coefficient of linear expansion. The larger the coefficient of linear expansion, the more the change or the more the deformation when you change the temperature. Okay, I hope that is making sense. So if you have alpha is equal to 24 times 10 to the minus 6 okay, and then another material has alpha is equal to 12 times 10 to the minus 6, and so on and so forth, then the alpha that is the largest will be to the material that stretches the more for the same change in temperature. Okay, so if we change the temperature by 5 degrees, the one material will stretch more than the other because its value for alpha is greater than the other material. Okay, so you have to understand that alpha is a property of the material. It is not the same value for all materials. The materials that deform more under a certain change in temperature will have a higher value for alpha than those that deform less. Okay, I hope I am making myself clear. And so this is the equation you use to find delta L, okay? And so therefore the final length, you will find it using this equation. It's going to be equal to the initial length of the bar plus the change in length due to the increase in temperature, okay? And this equation applies also when the change in temperature is a decrease in temperature. You will still use this equation, only that the value of delta L that you will get, now you will have to minus it here, okay? Because if you are decreasing the temperature, of course, the bar is not gonna get longer, but rather it will get shorter. So to get the final length when you're dealing with a decrease in temperature, you will need to do minus delta L. Okay, so all of this here is stuff from engineering science N4. And before I go on to the next slide, I just want to remind you of some of the things that we did in the first module. If you haven't watched my presentation on that module, it is available on YouTube. It's a 2 hours video. Just go ahead and watch that because you will need some of that knowledge to be able to tackle questions from this module. Okay, so this is just as a recall. Okay, when you have a force that is applied to bars in series, what did we say? We said that the deformation will be equal to the sum of deformations. Okay, so if you have two bars that are connected in series or mounted in series, the total deformation of that compound bar will be equal to the deformation of the first bar plus the deformation of the second bar. That is the case when the two bars are mounted in series. And the second thing to remember is that the force is the same. Okay, so the force in the first bar will be equal to the force in the second bar, and that will be equal to the force that is being applied to the compound bar or being applied on the compound bar. Okay, very, very important to remember this. And so from this equation, we can write this like that. You will remember that x, the elongation or the shortening, is equal to FL over AE. Okay, it is an elongation when the force applied is a tensile force, and x is a shortening when the force applied is a compressive force. Okay, but the equation is the same. Okay, so in this case, xt will be equal to F1L1 over A1E1 plus F2L2 over A2E2. And from this here, okay, you can see that F1 over A1, that is the equation for the stress. So you may actually be able to rewrite this equation like that, okay? So you can say xt will be equal to sigma 1, which is F1 over A1 multiplied by L1 over E1 plus sigma 2, which is F2 over A2, then multiplied by L2 over E2, because stress is equal to force over area. Okay, so all of this is just a quick recall, and the reason I need to do that is because we're gonna need some of this knowledge to be able to tackle questions in this module. And then you have bars in parallel. When you have a force that is applied to bars in parallel, the total deformation of the compound bar is equal to the deformation of the one bar, and which is equal to the deformation of the other bar. Okay, because the bars are parallel, Therefore, they all deform the same way. And bars in parallel can either be two bars next to each other, or they can be one bar inside of the other. Okay, that is what we mean by bars in parallel. So when you deform them, they both deform by the same amount. Okay, so the deformation of the compound bar is equal to the deformation of the first bar, which is also equal to the deformation of the other bar. Okay, so it's very important to remember this. And in this case, when you have a force applied to a compound bar where the bars are in parallel, then the total force applied is equal to the sum of the forces in each of the bars. Okay, so F is equal to F1 plus F2. Okay, which is different to the situation when you have bars in series. And so from this here, X1 being equal to X2, we can write this like that. Okay, and generally with bars in parallel, the length of the bars are equal. Okay, so L1 is equal to L2, which then means that we can simplify this equation to something like that. Okay, because L1 and L2 are going to cancel because they are equal. And then again, F1 over A1 is sigma 1, F2 over A2 is sigma 2, because stress is equal to force over area. Therefore, this equation here can be further simplified to something like that. Okay, so all of this is just a recall from module 1, where we deal with stresses and strains and so on and so forth. Okay, very important to remember these things. Now, these equations that you see here are valid when you're dealing with a situation where it is a force that is causing the stresses. It is a force that is causing the deformation. But in this module that we're doing, we are going to deal with deformations that are caused by temperature. Okay, and so I am going to give you all the knowledge that you need to have for you to understand how to get the stresses that are caused by temperature. Okay, you do not use this approach. This approach is only used to get the stresses that come from a force that is applied. Okay, but there is a different approach and different sets of equations that we're going to look at to find the stresses that arise from changes in temperature. So now we will begin by looking at bars in series. When you have bars in series with an increase in temperature, okay, a situation where you have two bars that are in series and then we increase the temperature. What are the equations that we're going to use to be able to calculate the stresses? This is what we're going to look at. So now look at this figure that you see on the screen. So you have this bar here, which is bar 1, and its length is L1. L1 is the initial length of bar 1. And then below it, you have this bar, which is bar 2, and the initial length of bar 2 is L2. Now, if we increase the temperature, okay, because we're dealing in this case with a situation where we increase the temperature. So now, if we increase the temperature, what will happen to bar 1? Bar 1 will stretch by this amount, delta L1, okay? This is the amount by which bar 1 is going to stretch. Okay, if you increase the temperature of this bar 2 by the same increase in temperature, bar 2 stretches by this amount, okay, delta L2. Okay, so you can see how these two bars would stretch if we increase the temperature. Now, let us suppose that we put now these two bars like that in series, okay? So they are now joined together. They are no longer free to stretch freely, but they are joined together. And then we increase the temperature again by the same amount as we did previously. Now you will find that bar 1 is not going to be free to stretch by all this, because bar 2 that is here will prevent it to stretch by this full amount. And in the same way, bar 2 also will not be free to stretch by that whole amount, because there is bar 1 here that is preventing